And today on the ONS podcast, we have my good friend Kevin O'Hara. He is a professor within mathematics, physics, and quantum mechanics. And today we were talking everything from astronomy to quantum mechanics and everything in between. It's a fascinating conversation, and I hope you enjoy it. I really am interested to talk to you about the main reason why I brought you on was to talk about the James Webb telescope.
Yeah.
This has been, like, those pictures have been messing with me for the last couple of weeks.
Oh, wow.
And, you're one of the few guys that I know that's kind of an expert in a lot of this, like, the area of science and space and all that kind of stuff. So kind of help me understand, like, what the hell are we looking at?
Okay. Well, I don't know which images you're referring to.
So there's the one that's messing with me the most is the one that shows, like, the picture of all the galaxies. Some of them are like warped into like a curvature, and it's just like what I had read. And I talked to Dr. Troy last week, and we were talking philosophy. And basically what NASA had put out was, if you hold up a grain of sand to the night sky with your arm stretched out, what that grain of sand is covering in the night sky is what that picture is. So that is only covering that much of the night sky.
Yeah, I think that might be a little bit of an exaggeration.
Okay.
It's a little more than that.
Okay.
It's more like, I think, like a thumbnail.
Okay.
Okay. So, but yeah, it's a very, very small patch of the sky, and it can see so deeply that it just picks up so far back, and so almost the entire night sky, or that little area, is just covered with galaxies that are various distances away. The thing about the James Webb is its primary design, what it was designed for, was to study the origins of the universe. Okay, and so what it needed to do is it needed to see way, way, way back in time. So the speed of light is 186 miles per second, and so as the universe expands, and galaxies get further and further apart, what happens is that the light waves that travel through that space get stretched out with space as it goes. And so they get stretched out into, from their normal wavelengths, they get longer and longer, which pushes all of them in the direction of the infrared. Okay.
Because it is an infrared image, correct? So, and then we're putting colors as we see them on.
Yes, we are. Now, the James Webb can see into the visible spectrum.
Okay.
The lower end of the visible spectrum, it can see into that. I think, let's see, the visible spectrum goes to, I think it's about 700 nanometers. And James Webb can see wavelengths down to about, I think, 600 nanometers. So it can see a portion of the visible range.
Okay.
But then it goes way down into the infrared, like way, way, way beyond what human eyes could see, the visible spectrum. So, and that's where these wavelengths of light actually are. So when you're looking at a galaxy that's, let's say, 13 billion light years away, you're seeing it as it looked 13 billion years ago. Okay?
Right.
So you're seeing how the galaxies formed at a very close approximation to the beginning of the universe. Okay? So you're seeing like the very first galaxies as they were forming. But to see that far away, because with the expansion of the universe, the light was stretched out into the infrared, you can't see those galaxies in the visible spectrum at all. So those galaxies, the galaxies that the James Webb can see, are Hubble is completely blind to them. It can't see them at all.
When was Hubble launched? When was it created?
It was launched. I can't remember exactly the day. I'm pretty sure it was in the early 90s when it was launched. I think it was actually closer to 2000, because I think 2020 was like its 20th anniversary, right around. Right around 2000. So it's either late.
We're working with like 90s tech, basically. That's right. We are. I mean, in terms of
I mean, the James Webb is light years beyond Hubble. I mean, first of all, its diameter is like 7 meters, and Hubble's is in 2 something. So, I mean, its diameter is 2.5 times what Hubble's is. So, I mean, that alone makes it fantastically more powerful in terms of what it can pick up. But in terms of the infrared, so that means it can see galaxies just way, 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 way beyond what Hubble could have ever seen. And not only can it see them, but it can see them really well.
Right.
And it can can use spectral imaging to determine the elements in that light. Sorry about that.
Yeah, it's all good, man.
So it is going to, all expectations are that it will revolutionize our understanding of the origins of the universe. I mean, it's just going to get mountains and mountains of data that we have had none of yet.
Right.
So yeah, it's powerful.
So you, as a professor in mathematics and science, dabble in the quantum physics and all of that. What do you, when you see that picture? Because to me, it was a terrifying picture. Like, it really kind of like messed with me a little bit.
What was terrifying?
More of like an existential crisis of like, how fucking small are we? Like, like Troy likes to tell his wife, like, I don't think we're supposed to see this. I don't think this is something we're supposed to see, because it's like, it starts to like make you question like everything you know to be true about your life and about spirituality and about science and all these kind of things. And so, but that's me as the layperson with no experience in science and mathematics. Like, what do you see? Like, what are the feelings you see when you see that?
Well, I mean, there's no question that we are unimaginably small in both space and in time. So space-time is, I mean, it is a vast cosmic sea. And we're just, I mean, I can't even think of an analogy. I mean, imagine yourself out in the middle of the Pacific Ocean somewhere, and you're in a little dinghy, and you look over on the water, and the sunlight going into the water, you can just barely see, like, as the beams of light go into the water, little tiny particulates, floating in the water, so our whole solar system compared to the universe would be way, way smaller than that little particulate there floating in the Pacific Ocean,
Right.
So, yeah, we're unimaginably small. But, I'm not sure that, I'm not sure that the size of things and numbers, what does that really, what should we infer from that? And I'm not so sure that we should infer that our smallness equates with our importance, right?
Right.
So
go on that.
Yeah. I mean, like, if you want to talk about things like, let's say, complexity, for all that we know, the most complex object that we know of in the universe sits between our ears and behind our eyes. I mean, it's this piece of gray matter that is just really so complex that we don't really understand it, and we all carry it around with us. And right now, to the best of our knowledge, there's nothing else anywhere in the universe that's that complex. And with that complexity, we have created both what may very well be the coldest place in the entire universe right here on this planet, and the hottest place in the universe right here on this planet. So, we might be pretty special.
Right. Well, I mean, so far we haven't found any life.
Right. And that, that's the other thing that the James Webb, is going to be able to help with. Because,
really?
Yes. Oh, absolutely. That's
in what way?
That wasn't the original design, but as they were designing it, and we were discovering. So when they first started designing the James Webb, I don't think we'd found any exoplanets yet. I think the first exoplanet was like, I don't know, 1995 or something is the first one that we found. But there was like a tipping point. of the technology and everything, today we know of 5,000 exoplanets.
And exoplanets are planets that can
around other star systems, so outside of our solar system.
But can sustain life or not necessarily?
No, we don't know that.
Okay.
I mean, that's we just know that the planets are there. Okay. So, so when we realized that, oh my gosh, like practically every star, statistically speaking, has planets around it, then we started looking for the stars that have planets that are in what's called the Goldilocks zone, like where life could be, at least life as we understand it, would have a reasonable chance of living there.
Right.
And, we've found lots of those, small, rocky, in the habitable zone, a lot like Earth. And so, then the very next thing was, well, how can we try and figure out if there is life there, and so one of the ways would be if we could examine those planets' atmospheres, because there are certain gases that would exist in an atmosphere. So namely, the big ones would be oxygen, methane, ammonia, CO2, and water. Okay, so those five, they are the telltale signs of life. I mean, in fact, as far as we know, methane, maybe the only way methane gas is produced is through life. Through life, yeah, right. Through metabolic processes and also decay of organic material. They believed that there was a geological way that methane could be created in small amounts, but now recently they've started studying that, and they're not sure. They're not 100% sure. They think that there were microbes that actually kind of got into those rocks and laid down certain precursors
which would be considered life.
Right, which would mean that, okay, maybe there's no way for a planet to have methane in its atmosphere unless it had life. Oxygen is a big one because oxygen as a molecule is extremely reactive. And so any planet that somehow obtained oxygen in its atmosphere where there was nothing on that planet producing more oxygen, that oxygen would just react with things and disappear. It would become other molecules and so forth. And so for there to be sustained oxygen in an atmosphere, although there are possible other processes that might make that happen, life would be the most natural thing. Ammonia is also a metabolic process that doesn't really, I'm not sure that there's any other way that it can be created naturally. So there's a number of those. So, and then of course water.
Right.
Okay. So if there's water, oxygen, CO2, which is also a gas created, I mean, that can be created through geologic processes. But if there's CO2, oxygen, methane, ammonia, and water, those five, especially in the right combinations, would be pretty much a slam dunk. Right. It would be almost impossible to imagine that anything else could create that combination of gases other than a diverse ecosystem.
Right.
Not just, not just single-celled organism, but a diverse ecosystem. So
this is blowing my mind right now.
And so James Webb.
Right.
Okay. So the point is that James Webb has some limited ability to actually look at exoplanets and actually understand the light that's coming from that planet's star, but moving through its atmosphere.
Okay.
Skimming through its atmosphere, and then examining that light for the telltale signatures of those certain gases. So that's the other thing it'll be able to do. So that's kind of exciting.
Right, and Hubble wasn't able to do that?
No.
Okay.
Hubble just didn't have the equipment to do it.
Right.
Now there's another telescope going up, I think in the next few years. It's called Starshade, and basically what it does is it blots out the light from the parent star of that planet so that it can see the planet directly. Oh. And then examine the light directly right off of through the planet's atmosphere, and so that'll be amazing.
How long? So the James Webb, where is it in space?
It's at a place called Lagrange 2, L2, and so basically, if you imagine the sun's here and the Earth is orbiting the sun, right? So there's a spot out in space out here where that the combined gravity of Earth and the sun would keep the James Webb in an orbit such that it goes around the sun with the same period as the Earth. So it's always behind the Earth in line with the sun. So as the Earth orbits the sun, the James Webb orbits the sun at exactly the same amount of time.
Is that to block out the sun's light? What is the purpose of that?
Well, no, it's actually Lagrange 2. It's like 900,000 miles out.
Oh shit! Okay.
Yeah. So at that distance, looking at Earth, you'd still see the sun.
Right.
It has a sun shield.
Okay.
So basically, what it does is it has this big, huge sun shield to block out the sun. Now, the reason it has to do that is not because the light coming from the sun would interfere so much as it is that the sun will warm up the telescope itself. And so when it warms up the telescope itself will start emitting infrared energy, which would just wash out the infrared light coming in from what it's trying to look at. So the James Webb has to be kept at near absolute zero in order to see the infrared images coming in. And so in order to do that, it has to block out the rays from the sun with the sun shield so that the sun doesn't heat up the James Webb itself. Gotcha. Okay, so that's why it has a sun shield. And the engineering for that,
you as a mathematician and a physicist, like, you have to, like, you appreciate that so much more than, like, the average guy, because it's like you understand the complexity of what they just accomplished. And that was kind of one of the conversations my wife and I had about, like, this is so fucking cool.
Yeah.
Like,
it's
like humans are amazing. Like,
oh my God.
Not to, like, toot our own horn, but the fact that we are, like, so curious and have taken our abilities in science and mathematics to the point to where we can do something like this.
Yeah.
And it's incredible.
Here's a good example. Okay. So the James Webb, it's sitting out there, it's looking out into space, right? So if you could, like, take like a BB gun and fire a BB into space, the size of a BB, right? And it was at room temperature, let's say. Okay. And you fired it, and so it's moving at an angle, and it moves in front of the field of view of the James Webb, and it's at room temperature, and it's 1,000,000 miles away, light up like a Christmas tree for the James Webb.
Wow.
At 1,000,000 miles away, you could see a BB at room temperature. So, that's pretty astounding.
Right.
Yeah.
But that's where it's like, stuff like this, like, fascinates me. And, like, when I see you, every time I see you, I'm like, I got to talk to Kevin about this stuff, because you're the only person in my life that I know that actually knows what they're talking about when it comes to things like this.
Yeah.
And we've had long conversations about quantum physics and all of that. And we can get into all of that, like what it makes you feel like when you see something like this is
right.
So what, like, initially, like, what got you started in this area, like, of physics? Like, what piqued your interest?
That's a good question. When I was a young guy, I was in a band, had long hair, sex, drugs, rock and roll. That was me. I dropped out of high school. I was kind of like the rebel type, My father was a minister. But I always questioned. I had a natural intellectual curiosity, and I questioned a lot of things, questioned theology, the existence of God, all of that, And one day, sitting at an airport, I think I was 17. I was actually coming home from my grandfather's funeral. He had passed away. He lived in Ohio, and I was coming back to Florida, and I was by myself. And I went into the bookstore, and I was always like a Star Trek fan. I was always into, like, sci-fi and that kind of thing, and I liked the subject. So I knew a lot about science even then, even when I was, you know, a rebel or whatever. But I just saw this book by a guy I'd never heard of before. His name was Stephen Hawking. And it was called A Brief History of Time.
Right.
It's his first book. And I bought it, and, you know, I just started reading it, and I was just riveted. I was spellbound, you know. And, you know, because I was into theology in the sense of I want to understand, you know, can we prove the existence of God, or, you know, and in that book he used the phrase God a lot, and he did so in the context of talking about, you know, how designed the universe looks, and that's still true today. I mean, the universe does look extremely designed, and even designed for like life, you know. And so, I mean, that just fascinated me, and it made me think, okay, maybe there is a designer. I'd kind of settled on atheism at that point in my life. And so I thought, well, maybe there is something. So I was actually a music major in college because I was in a band and all that. And I literally decided, it changed my life. I literally
changed.
One book. Yeah, that one book changed my life, absolutely. And so I changed my major from music to physics, actually, you know. Had no idea. I didn't even know that I needed to know a lot of math, okay, to do physics. I mean, I you know, it was, I mean, so the amount of math that I had to take was enormous, you know.
Right.
So, you know, and I didn't know any of that. And then there was another event that also took place. I was taking an astronomy class, and in the astronomy class, you know, there was one point where we were talking about something called quasars, and so I wrote this paper on them. You got like extra credit for writing a paper on something, and I wrote this paper on these quasars, and, you know, as was usual for me in those days, I was half BSing my way through the paper,
sure,
right?
Yeah,
and
like we all did in school.
Yeah, right. And at one point in the paper, I made this comment. Because I knew the universe was expanding, and way off, it was like expanding at like, you know, 90% the speed of light. So quasars were moving away from us at 90% the speed of light. And so I made this comment that I thought was common sense. I said, you know, so the light coming to us from those quasars is only moving at 10% the speed of light, right? And I forget why I made the comment, but so later I get the paper back. He gave me like a B+, you know, and everything. And I went to him to talk about it, and I happened to mention that. He said, "Oh yeah," he said, "that's actually something that you said that's not true at all." And I said, "Well, what do you mean that's not true? It's like, I mean, quasars are moving away from us at 90% the speed of light, right?" And he said, "Yes, that's true." I said, "Well, so then the light coming off of them must only be approaching us at, you know, 10% the speed of light." He said, "No, that's the part that's wrong. You know, it's approaching us at the speed of light." And I said, "Okay, wait a minute. How can that be true? I mean, it's like, you know, because, you know, if I'm on a train car and I'm moving 50 miles per hour and I pitch a baseball at 60 miles per hour, I mean, along the ground, it's only going to be going 10 miles per hour, right?" And I said that to him. He said, "Yeah, but it doesn't work that way with light. Light, all observers see the speed of light as the speed of light, no matter how they're moving relative to it." I said, "Okay, wait a minute. Hold on. So wait, you're telling me then, if I was in a spaceship and I could go at 90% the speed of light, and someone at a stationary space station fired a laser in the direction of my ship, as that laser beam passed the window of my ship and I could measure it, you're telling me I would measure it going by me at the speed of light?" And he said, "Yes, you would," which blew my mind. He said, those are the consequences of relativity. That's Einstein's theory of relativity. And I said, "How could that be?" And he said, "Well, it can be because as you're moving, as you get closer to the speed of light, time in your ship slows down. Time is not moving at the same speed." And I said, "Wait a minute, you mean so if I like travel close to the speed of light for a long time, I like wouldn't age as fast?" He said, "No, you wouldn't, because time wouldn't go by as fast." And then he said, "You know, if you got into a spaceship and, you know, you left it at the speed of light, or like at 99% the speed of light, you know, and you traveled for, you know, several days out and then came back, even though, you know, only 3 or 4 days went by for you, you would find that hundreds of years went by on Earth." And that blew my mind.
Right. I mean, it's like the movie Interstellar.
Yeah,
like,
right.
Yeah,
that's exactly right. And so that did it for me. I mean, the combination of those things, I was just enthralled with that, and I just had to understand it. And so then that's launched me on, a 25-year journey. So that I got my degrees in math and physics and so forth, and I was a pastor, and so I wanted to study, the theology and science and how they might complement each other and that kind of thing. So that then allowed me to really just stay on top of science in general, not just in physics. A lot of cosmology, a lot of biology, evolution, that kind of thing. So, I learned a lot about that stuff. And yeah, definitely the more you learn, I mean, the universe is really, one scientist put it, the universe is not only stranger than we've imagined, it's stranger than we can imagine.
Right.
So, and that kind of turns out to be true.
So when you, obviously, because this is your field, this is what you love to do, and you obviously have a lot of experience in that. What gives you? I'm trying to phrase this question right. Because of your background within theology, but also the understanding of how the universe works, or as much as we can know, how are you able to kind of marry the two? Because there seems to be a lot of design to the universe. Yeah. But there also seems to be a lot of random and chaos, randomness and chaos to the universe. Right. No question. I think it was Christopher Hitchens that, who's a famous atheist debater. Right. And I actually really, really love a lot of his work. I thought he was just a brilliant mind. Right. But he would talk about, like, if there is a design to this whole thing, why do we have so many flaws, even in the human body? Like, we have so many flaws that don't seem designed. How are you able to, like, marry the two together? Because they seem like conflicting ideas.
Yeah. Well, first I would say that the traditional religions of the world, including Christianity, which I was, a pastor in, and many of the claims of those adherents to those religions. So in modern times, evangelical pastors here in America, the claims that they make about Christianity and the subsequent claims about reality, then a great many of those claims are provably false. Provably false. They don't know that, or they won't accept it. A lot of it has to do with the fact that they just are ignorant of the discoveries of science. And a lot of these are just discoveries of science. And there are things that just cannot be true, literally. Okay. So let me just say that, a lot of that just has to go in the waste can. Okay. Now, then, though, if you say, okay, so, if I wanted to retain some notion of a creator and some notion of a creator with some sort of, supreme intelligence of some kind, what does it take for that to be true? So when I examine that, when I go through with all of my understanding of science and philosophy and theology, when I go through that, I find, the short answer is that I find that reality with something like a creator with some sort of supreme intelligence seems to make more sense and answer more questions than one without. Okay. So that's what I would say. So if we were to talk about that, I could give you my reasons for that. Understand, though, I'm not at all saying that I think that, God has a plan for your life. And no, he doesn't. Right. There's no plan. There's not a plan. Okay. Your life is governed mostly by randomness. Right. Okay. It's more governed by randomness than any other single thing. Now, thankfully, the advent of modern science and the technologies that it's producing is making that so that is less and less true. Okay, so people who lived, 5,000 years ago basically had no options in life at all. I mean, they were completely at the mercy of
nature,
yeah, pretty much.
Yeah.
Okay,
Dying of tooth decay,
exactly right.
Getting mauled by a tiger.
Yes, and today we're getting much, much, much better at actually giving us some things that we have control over. But with all of our advances, as an individual, the thing that has more impact in your life as a whole than any other single factor would be randomness.
Right.
So yeah, there's not, and that's provable. You can prove that basically with modern statistics. You can prove it. Okay. So yeah, there's not a plan. And now, unless you want to say that there's
the plan is there is no plan.
Well, yeah. Well, you could think of in terms of like, okay, there is a plan that includes randomness.
Right.
Okay. So yeah, there is a plan that necessitates the need for randomness, and even randomness, you can count on randomness. I mean, there's probability theory, right? So when you have large enough numbers, you can be guaranteed pretty much of certain outcomes, even though each individual event would be random.
Right.
Okay. So, yeah, I mean, there's lots of things like that where, if you just take a deck of cards, or if you flip a coin, it's 50-50 chance of getting heads or tails. But if you flipped a coin 4 times, the probability that you get all heads is like 25%. Okay. But if you flip it 1,000 times, the probability of even getting 600 heads becomes almost non-existent. So there's a sense in which probability and randomness can kind of come together to kind of create actual outcomes that make sense. I mean, so all of the biological processes in our body, all of them are random.
Right.
Okay. But there's so many of them, and they're random in just such a way that a pattern emerges, which creates life. So, just because there's randomness, that doesn't exclude the notion of some sort of really big sort of overarching plan for all of reality, let's say.
Okay.
But I think it does exclude the possibility of individual plans for every individual's life. I think it does exclude that.
Gotcha. So how does the simulation theory work in that? I mean, I'm sure you've heard of that.
Yeah, absolutely.
Yeah.
I don't believe in it,
okay.
And there's a reason. I'll explain that reason.
You're going up against my boy Elon Musk.
Yeah. I think he's dead wrong,
okay.
and he hasn't. There's certain things he hasn't thought of. Okay. So the idea first, the argument is that we look at ourselves and we're creating simulations on computers, and some of them are very, very lifelike. And you can sort of get the computer to run its own simulations. Yes, you can definitely do that. And you can even program computers to run simulations where that randomness is involved. Okay. And it can create these very complex structures and everything. And so the argument is, well, if we are doing that, then how do we know we're not a simulation on some really advanced computer or whatever? Okay. So my argument against that is that the first thing that assumes is that consciousness, as we understand it, can be simulated. Okay. Now, the famous physicist Roger Penrose, who, by the way, just won the Nobel Prize in 2020 for his work on Big Bang cosmology and black holes, one of the most brilliant physicists of our generation, no question about it. He wrote a book on that subject, and he basically lays out the notion that discovering truth is not, or the understanding of why something is true is not an algorithmic process. So in other words, it can't be simulated. It can't be. And there's a lot of things I could tell you to look up that are related to it. For example, the girl who does the podcast Up and Atom.
Okay.
She does a really cool podcast, or one of hers is on computers discovering truth. Okay, and so it turns out in the last century that mathematicians were a big part of this. That because mathematics, the undergirding, what upholds mathematics is pure logic. Okay.
Okay.
And so in logic, you can do demonstrations where that if your premises are true, the conclusion would have to be true.
Okay.
Okay. And so the thought was that then when you actually get into logic, you realize that you're just kind of shuffling terms. Okay, so you have these premises and you have these rules of logic, and you start doing this demonstration, and all you're doing is just applying rules, right? I mean, that a computer could do, right? You're just applying rules, and then the conclusion has to be true. It's not an opinion. It has to be true. If the premises are true, the conclusion has to be true. Okay. And so the thought was among mathematicians was, well, gosh, maybe then all true statements can just be proven. Okay, so we can just, if it's true, it can be proven, period, right? So there was a lot of investigation into that. And then along comes this guy named Kurt Gödel, who is a logician. And he basically...
Let me pause you real quick. What's a logician?
A logician is a mathematician who really studies what today we would call first-order logic. Okay, so it's fundamental logic. It's the foundation of all mathematics. Okay.
All right.
And he was able to prove that no mathematical system, given some set of axioms, which are like premises,
right,
no mathematical system, there would always be questions that you would want to know the answer to in that mathematical system that there would be no way to prove in that mathematical system. Okay. Now you could add an axiom at the beginning, and then it would make it so you could prove it. But by adding that extra axiom, you create now new questions and new theorems that you can't prove.
So like answering one question leads to two more, three more questions.
And
gotcha.
And the truth algorithm that she talks about in Up and Atom, same kind of thing. They thought, maybe there's a way to study complexity and you can do this thing on a computer and it could just shuffle the terms and it could do it, but it can't. And so what Roger Penrose did is he took that and he extrapolated and he showed, in specific instances, he showed where that there are certain mathematical proofs that we do that would be the same as saying that certain computations, if you set them in motion, would go on forever and ever and ever. So for example, we can prove that there's no largest prime number, that no matter how big you get, there's going to be another prime number somewhere down. Okay, so the computation that goes searching for prime numbers would go forever and ever and ever because there'd be no end to them. So proving that there's no largest prime number is the same as proving that a computation that looks for prime numbers would go on forever and ever, right? And so what you can do is you can show that, okay, so let's say I create an algorithm now, and this algorithm's job is to look at other algorithms and determine whether or not, given some input number, that algorithm will go on forever and ever and ever, or it will stop at some place. Okay, that's this algorithm's job. Okay. So the problem then is it's just an algorithm, right? And so you can feed it programs, which are just algorithms. So it's an algorithm that analyzes algorithms, which is an algorithm itself. So it can, presumably, any algorithm you put in, you can just put it in there, right? And it figures out whether some algorithm will halt or go on forever and ever. So now what happens if you take its algorithm and give it to itself? What happens? Well, if it determines that it goes on forever and ever, then it's... I neglected to mention this. So what this algorithm does is if it determines that another algorithm goes on forever, it stops. Okay?
All right.
But if it determines that this algorithm stops, then it will just go into a loop and go forever and ever. Okay? And so you could easily program that.
Right.
Okay? So then if you feed it its own algorithm, then if it discovers its algorithm goes on forever and ever, it stops. And if it discovers it stops, it goes on forever and ever. Do you see that there's a fundamental contradiction there? Okay, and so so that program fundamentally cannot exist.
Okay.
Okay. And the same thing was discovered in mathematics with set theory. So the idea of a set is a collection of objects, and we basically when you use sets, you can apply logic very well to sets. And so that's why everybody likes sets. But the problem is you can create sets that can exist. So for example, if you were to say, the barber in a town shaves every man who does not shave himself and doesn't shave anyone who does shave himself. Well, on the surface, that looks like an innocent statement, but then you have to ask, well, who shaves the barber then? Right? And so that's a set that can exist.
Okay.
Okay. And that was one of and that's what Gödel actually showed.
Okay.
Okay. So what Roger Penrose was able to do was he was able to say, look, this would apply. You wouldn't have to necessarily feed the algorithm itself. So he showed that there would be algorithms that if it could do that, if it could show that other algorithms go forever and ever and ever, you would create a contradiction. Okay. And he showed that specifically with certain calculations. But when you and I, or a mathematician, proves that, let's say, there's no largest prime number, what we've just done is prove that that algorithm would go on forever and ever and ever. So we seem to be able to do it, but algorithms can't.
Okay.
And so so the problem with that is I don't think that consciousness, as we understand it, is algorithmic.
Right. Well, that was my question, because I understand, as far as the AI world, their biggest problem with any sort of AI, and if you talk to most of the guys that are in AI, they're not super concerned with sentient AI or conscious AI, because we can't
really understand it.
We don't understand it. We barely understand our own brain.
We don't understand that at all.
So it's so they seem to be less concerned with any sort of sentient, how do you program consciousness, and how at what point do you when is an object or a being or even an animal, at what point do we say this is a conscious being?
Right. It's a good question. I mean, what Roger Penrose would say is, well, now this is a very specific thing,
right?
But he would say, okay, well, if you can ask the computer to give an original proof to a mathematical proposition of the kind I've demonstrated,
right,
and it could do it, well, then it doesn't seem to be anything it can't do that consciousness can do.
But would that be the only marker for consciousness? I mean, don't we have other more emotional markers for consciousness, fear of death? A longing for goals. A lot of other things that we kind of do as humans, that we've placed consciousness and we've given it an idea, this is what consciousness is, which obviously is a man-made construct. How do we? At what point do we state oh, this thing is now? We did it. This AI is conscious. It's a sentient being.
I mean, that's a good question. Okay, so back to that original thing about are we, a simulation. So the reason I would say for all practical purposes that's not true is because when we can discover truths of the kind I'm talking about, so discovering that there's no largest prime number, that is a truth. That is something that would have to be true of any possible reality.
Okay, and why is that?
Well, because once you just define what integers are and you define what a prime number is, then prime numbers will go on forever and ever and ever once you define the mathematical term. So there's no universe in which you could have, let's say, a universe that has an infinite number of objects of a certain kind, in which you could make a big enough set of those objects so that no set bigger than that would ever end up being a prime number.
Okay.
That's not possible. That can't be true in any possible reality, okay? So that means I know something through my own reasoning. I know something not just about my reality, but any possible reality. So even if I were a simulation, I would know something about my simulator's reality. And if they were a simulation, about their simulator's reality, all the way up to the top reality. So there would be some sense in which my consciousness would not be bound by the simulation, because I would be able, through my reasoning, to ascertain things about the top reality, wherever that is. And so in that sense, there would be a sense in which I was on par with whatever consciousness was creating the first simulation all the way down. You see what I'm saying?
Yeah.
So so to me, that would be like if we could create an AI that really was conscious, whether it was in a body or just on a computer, there would be a practical sense in which it wasn't a simulation. Right? I mean, it would know as much about reality as we do.
Right.
And so what would we even mean by a simulation? We would just mean that consciousness as we have it can somehow be produced in ways other than the biological ways.
Okay.
That's all we would mean by that. So in what sense is it a simulation? So so in that sense, in the sense that like every decision that you and I make is just because of the simulation and the programming causing it, that I don't believe.
Okay.
Okay. So in that sense, we're not a simulation.
Okay.
Okay.
But so obviously within the one of the main like parameters of a simulation is that there is an ultimate creator, right?
Yeah,
because
right.
you would need the creator
Right.
to create the simulation. So
Right.
how is that any different than kind of what you believe as far as like we do have some sort of all-knowing, all-powerful being that set this all into motion? How does that conflict with that at all?
Okay, I'm trying to understand.
Because every time I see somebody talk about simulation theory, it almost feels like a creator.
Yeah, right.
So how are those two things different?
Well, as I said, I don't believe that we are creating genuine consciousness.
Okay. But there was a creator that created consciousness.
Okay, so that's an interesting point.
Right.
Okay, so what that would mean, so if consciousness can't be simulated, I mean true consciousness with
Right.
the ability to reason to truth.
I think, therefore, I am.
Yeah, well, that's more of an existence kind of.
Right.
C.S. Lewis, he put it this way with regard to reasoning to truth. So if our ability to reason to a true conclusion is based simply on, the random motion of atoms in our brain, or some simulation that's controlling every single step of it, okay, then that would mean that the conclusion that we arrived at that conclusion not because it was true, but because the simulation decided that we would arrive at it, or that the randomness of the universe, the state of the universe in our brain at any one time, decided that we would arrive at that conclusion.
Right.
But if that were true, then that would mean that we couldn't trust any of our conclusions, which would include the conclusion that we're a simulation, or that we're just, that the universe can naturalism, let's say,
Right.
is true. And I think that's intriguing. That's an intriguing thought. And from everything I've seen in quantum mechanics, Gödel's proof, Roger Penrose and his analysis of consciousness tells me, I believe that the reality that we experience, somehow it's not able to create consciousness the way we have it, the way we're able to come to conclusions that we know are true. And so it seems to me that maybe there's just a extra part to reality, a super reality,
Sure,
if you will.
yeah.
Okay, that maybe our reality is somehow enfolded into a higher reality. Okay, and I mean, string theory postulates some of that.
Yeah, break that down.
Well, I mean, in string theory, there's the idea that there's these extra dimensions.
Right.
And
Almost like a multiverse theory? Is
yeah,
that
the multi,
same?
yeah, and so one in particular that I'm kind of is in my mind as I'm describing this to you is the idea. It's called M theory. A lot of people say it stands for membrane. So, like, instead of a string, it's like a membrane,
Okay.
right? Like a drum head that vibrates instead of a string, right? And that what this membrane really is that it's a slice of the higher reality that it floats in, the slice is created by the absence of some of the characteristics of the higher reality.
Okay.
Okay. So, for example, let's say you've got
I am too damn stupid for this conversation.
So, I mean, imagine that, like, you've got this higher reality, I don't know, of 3 dimensions of space,
okay,
and a dimension of time,
okay,
let's say. And so let's say you have this membrane floating that's just space and there's no time. And there's a membrane floating that's just time and no space. And let's say they collide with each other, right? And so at that collision point, that's just a point. But then as they kind of move through each other, right, their intersection is maybe some sort of circle that gets bigger and bigger as they move through each other. Maybe that circle is our universe of 3 dimensions of space and time. And the reason it's expanding is just because the membranes are moving through each other. Okay. But then to get outside of that into this higher sort of reality, let's say, there would be other properties there. So maybe, 3 dimensions of space and a dimension of time. Maybe there's lots more dimensions out there that we just aren't even experiencing.
Right.
And so it seems to me that maybe there's a possibility that consciousness, as we're experiencing it, is a combination of the realities of this universe mixed with some portion of the higher reality. That maybe consciousness is like the one place where there's some extra characteristics that make it into our reality, okay, but nothing else. Okay. And so what we perceive as this consciousness, and part of the reason it can't be explained within our reality is because it would require elements from the higher dimensional reality that we just don't perceive at all. Okay? And so so maybe it's such a thing that consciousness is not the emergent property that it kind of appears to be, but that in fact it's a foundational property.
So then how would, say, humans have found or discovered or tapped into consciousness, but maybe not like certain animals or something like that?
I mean, I'm not 100% sure that, I think consciousness could just be on different levels,
Okay. So there's not any one thing
right.
That, this, like,
maybe it's just such a thing that certain components of our universe that when they come together in a certain way sort of allow the emergence of the sort of intersection of that. So it allows this emergence, and the combination of the two create what we call consciousness. But the more evolved that consciousness is, the higher it is. So yeah, there's a difference between dogs and us.
Sure.
But
well, there's a difference between us and the Neanderthals, like,
no question.
Right. So it's almost like it's not a singular point that it's discovered, but it's almost like a progression.
Right. Okay. Like so maybe our universe, the way the universe itself is evolving, is that there are components to its reality that, when are combined in a certain way, sort of allow or create or allow more components from the higher reality to intersect with it.
Okay.
And maybe one of those things that creates is what we call as consciousness.
Okay.
Right?
So because of our lack of understanding of this whole thing, like, how the hell do we replicate it if we don't even understand it?
I don't think that we can. So what I'm going to say, here's my prediction.
Right.
As a scientist, I'm going to make this prediction. This is what would prove me right or wrong.
Right.
Okay. If the day comes when we can create a computer that can do an original mathematical proof of the kind that Roger Penrose has talked about, you'd have me.
Okay.
I would say, okay, well, then we've created consciousness, because it can do something that I'm claiming only consciousness can do. Now, so maybe it can mimic a lot of things. And I think that Turing maybe had it wrong. Because he said his Turing test was, well, if you can talk to a computer, and no matter how long you talk to it, you can't tell that it's, you know, a human being on the other side of that door. He wasn't
Right.
thinking of an android at the
Right.
time, but you couldn't discover that it wasn't a human for all practical purposes. It's conscious. Well, but what I would say is depends on, you know, somebody like Roger Penrose would be able to ask certain penetrating questions that
Right.
most people wouldn't think to even ask.
Right, because
So-
the way that most of those programs, at least what we have right now as far as AI works, is that it's literally just pulling all the data
Yeah.
from the existing internet or
Right.
whatever, and then pulling those responses from that. So it's
Right.
not an original response; it's a response from the
Yeah.
experience.
It is it's doing like really powerful like statistical models, like almost so like it can see a pattern,
Mhm.
and once it sees a pattern, it can find certain similarities, and it can say, okay, well, when in the past when this pattern was here, here's what happened
Okay.
afterwards. Okay. And of course, it never forgets any pattern it ever sees, no matter how many millions of them it sees. And I mean, that's what happened with I think DeepMind. I think it was DeepMind that just beat not too long ago.
Oh, yeah.
The Go player.
Yeah, yeah.
And that was such a milestone because unlike chess, the number of possible moves in Go just goes up so exponentially
Right.
that no computer in the world could even begin to store every possible move. So what it had to do was, as it played itself millions of times, it looked for patterns. And in those patterns, it did statistical analysis then of, well, and this pattern is here, this is what happens next. And so in that first game with that world champion, it actually made a move that everybody thought, oh, that was a bad move. And then it beat him, that move. And in fact, there is a catalog of the most famous Go moves, like throughout history. There's this big catalog. And like once in a generation, a new move gets added that was like, oh, that move. Nobody ever thought of that move before. That was one of those moves.
Oh, wow.
And so, you know, but again, very advanced statistical models.
Right.
Never forgets a pattern. Can compare every pattern it's ever had before with the one it sees now and run statistical analysis. And so, yeah, it can't calculate every possible move, but it can say, well, you know what, 9 times out of 10, when there was this pattern or a pattern very similar to it, here's what it ended up, you know, this is what happened. And so it saw, well, if I make this move here, I'll have that pattern. And 8 times out of 10, when I had the player that had that pattern, when I played myself, won. And so it just made that move, you know?
That's so wild. Like
Yeah.
I mean, because at that point the computer's thinking for itself, it's not
Yeah.
a program. I mean, I guess it's a program, but it's like a human didn't tell it to make that move.
Right.
That
that's
computer
right.
decided to make that move.
Right. I mean, it is all self-contained.
In what
It
way?
is. I mean, it's self-contained in the sense that, you know, it's, you know, as it does things, as it plays itself and whatever, it stores in memory, it remembers all
I
the
got you.
patterns.
Got you.
And so, yes, it is all self-contained. And as the Sentry input comes in, the processes of the algorithms that are already just there
Right.
just happen. But at the end of the day, they're unthinking. No matter how complex it is, it just happens.
It's just following its algorithm. It's
Right, it
programming.
is, and that's right. And when
because
you-
somebody had to
Yeah.
go in and say, I'm going to program this computer to find all the statistical
Right,
plays
yeah.
that it can possibly. Okay. I get what you're saying.
Yeah. And so, and that's what Roger Penrose showed. He showed that understanding, like the understanding that this is true, is something that can't be algorithmic. It can't be. And so he showed that. And I think that's pretty impressive. He kind of showed it mathematically.
To kind of pivot a little bit, so where do you think DNA memory comes into play when it comes to consciousness?
Well, I mean, I think that DNA is an advanced computer, basically. I mean,
Right. But it affects, like, it's almost a part of our consciousness. And I kind of had this talk a little bit with Dr. Troy last
Right,
week, just
right.
as far as, like, if our DNA has a memory, like we've talked about this before, like humans can see snakes
Mhm.
better because of our long evolutionary
Yeah, that's right,
process.
right.
You know, there was he's an evolutionary psychologist, And he was stating, one of the theories for why children are afraid of the dark is because thousands and thousands of years ago, the dark meant you couldn't see the predator that was about to come and kill you. Makes sense.
Yeah.
But it's like those memories seem to be woven within our DNA.
Yes.
So the DNA is almost part of our consciousness.
Yeah, that's true. I think that's true. I mean, you can go further than that. If you read Dan Kahneman's book, Thinking Fast and Slow, I mean, he demonstrates that so much of what goes on inside of our minds is completely unknown to us. Like we don't know why we do the things we do. We don't know why we think we know why we make the choices we make, but we don't. And there are experiments that show that very clearly. Okay. So in that regard, there is a sense in which, if you look at that kind of evidence, well, it looks like we're just computers. That, that we just respond to our environment, period.
Right.
And that there's nothing about that. But see, here's the thing. Yuval Harari pointed this out in
Sapiens?
No, not Sapiens. It was the book after that, Homo Deus.
Yes, yeah.
And so he said, he talked about this idea of consciousness. He said, the more we've understood the processes of the brain and of biology and how mechanistic it is, the problem of consciousness has only gotten worse. Because, before, when it was all sort of vague, right, you could say, well, so I see a lion and I'm scared. Why am I scared? Well, being scared is an evolutionary advantage, right? You're scared, you run like hell. As soon as you see a lion, you get to safety or whatever, or you don't get the lion's attention, whatever, So that's an evolutionary advantage to be afraid, right?
Okay.
But so then as we understand how, photons coming into the eye and hitting the optic nerve and jiggling it and causing a cascade of neural activity and synapses firing, and then those synapses firing do something that somehow says we recognize a lion, and then those synapses fire down into our muscles, and those muscles then flex, and we begin to run in a certain direction, and all of that is what keeps this organism we call a human alive when it sees the lion. But if all of that can be explained purely from just the physics and the chemistry, all of these unthinking processes, why the feeling of being afraid? Why does that even need to come in?
Would it have to be something with the hormone release as far as like...
Well, but again, that's just a process of chemistry. So it's just all these reactions. And so, the running away from the lion, you can imagine things evolving in such a way that whenever there's sensory input from the environment, those cells react in a certain way. And they just do that because of their structure. And the ones who, evolve certain adaptations survive better. And so those adaptations are there, but it's still just chemical reactions and nothing thinking there. And so the question is if everything about me, if the light coming in from that lion's body that goes through my eyes and causes a cascade in my brain, and if all of that can just be decomposed into nothing more than the laws of physics and chemistry unconsciously acting through evolution, then this thing called my body is doing what it needs to do to survive and not be torn apart by that lion, just like single-celled organisms do. Okay? So why do I need thought or emotion or fear or any motivation? Why are those feelings even there?
I get what you're saying.
And he points out, no one knows that.
Yeah.
No one understands that at all.
Right.
The same thing with how is it, if our brain is just a collection of atoms, how is it that we can do mathematical proofs that no algorithm seems to be able to do?
Right.
The algorithm, the computer is just a collection of atoms. Why can't it do it? And so that's the problem with consciousness. But yeah, I admit there's lots of evidence that seem to suggest that much of what we do does happen on sort of a subconscious level, and that we're not in control of it. And in that regard,
it's like the only thing we understand less than consciousness is the subconscious. Like,
yeah, I mean, it's why do we dream at night? It's just
that's something that I can't remember where I was listening to, but that's just something that we've kind of accepted as like a thing that we do. We enter an alternate reality when we close our eyes.
Yeah,
and it doesn't. It's like it's shared and lived experiences, but it's also not shared and lived experiences. And then you throw psychedelics into that, and it's just like where the hell do you go? I don't know if you have any experience.
And it's
with
bizarre because and we have figured out like there's like a region in your brain that we call the fact-checking region.
Okay.
That it seemed, at least, in all of this,
very scientific name,
right? Yeah, right. I mean, all of this. The thing is I can't remember his name, but there's a guy who's his whole scholarly study is about reality. What is reality? And what is consciousness? And he says the problem is that we don't even know what reality is, and he believes that reality is like a hack. He thinks it's like in some ways it's he does think it's kind of a simulation. So he thinks that what evolution gave us was ability to sort of hack reality, not see it for what it really is. And he gives lots
Keep
of
going with that. Yeah.
Well, so like for example, certain insects. There was an insect in Australia. He gave this example. It almost went extinct because certain beer bottles in Australia had these little divots on them that when the sun glimmered on it, made it look like the back of a female of its species, and it kept trying to mate with the bottles. Okay. And so his point it didn't know the difference between the bottle and so there were certain things that happened. And he says that that's true of us, that the things that we say are real are really just, they're like shortcuts. They're like ways of us sort of getting by, but they're not the actual reality. And he goes so far as to say that, so people say to him, well, if reality, if it's not real, then why don't you step in front of that speeding train?
Right. Yeah.
And he says, well, because he says, I wouldn't step in front of that speeding train for the same reason I wouldn't take an important document on my desktop and drag it into the trash. The icon on my desktop is not the document, okay? But it's a representation of the document. And if I drag it into the trash, I will lose it in a real sense in reality, right? And so even though the train is not actually reality, me stepping in front of it, it's an icon of reality. Mm-hmm. But if I take certain actions with regard to that icon, certain bad things will happen. Okay. And so, this is reality giving me my hack. And he says it's not that, well, yeah, this table looks real, but really it's made up of atoms and so forth. And so, yeah, we're not really seeing reality for what it is. He says, no. Even the atoms are just hacks. They're just representations. They're icons on a desktop of reality. And we don't know how to get underneath that desktop. And so one of the things he points out about consciousness is all the experiments you do that show like some sort of correlation, you have to remember one of the first rules of science is that correlation does not imply causation.
Okay.
So just because there's a correlation doesn't mean that there's a causal factor there.
Sure.
So a great example is, if you could take a camera video footage of, like, let's say a train station, right? And, when you watched it, what you would see is it's empty, and then people start showing up, and it starts to get crowded. And then when it gets crowded, all of a sudden a train comes, and people get on it, and it goes away, and it's empty again. And then some time goes by, and nothing happens until people start showing up again, right? And then lots of people show up, right? And then the train comes again, right? So the question is okay, I mean, one conclusion you could come to is, well, people coming to the train station causes the train to come. But that's not true.
Right.
Okay? There's a third cause, namely the schedule. And both of them are following the schedule.
Right.
Okay? The train is supposed to be at this place at a certain time. The people want to catch a train. And so the schedule is doing that. One's not causing the other. And so so he points out that just because we may see something that goes on in our cognition, and then something happens, a moment later. Just because we see that correlation, that doesn't mean that there was a causal factor there.
Right.
Okay. So because some experiments can show under certain conditions that if you take very simple choices for people and you say, okay, you're going to choose this, you're going to choose that, that if they're hooked up to to electrodes and so forth, and it's hooked up to a computer, that the computer can start to anticipate what choice they're going to make before they make it.
Oh shit.
Okay. And it can even apparently it can even do so before they're aware that they're going to make it.
Is it because of the certain like neurons firing within the brain? Like how the hell does it measure that?
The thing is I want to go do it because what I want to show, what I believe I could do, I believe I could fool it. I believe I could make the computer say I'm going to make one choice when I make another one.
And how would you do that?
Well, that's complicated, but what it's doing, it's very simple choices. So basically, it's saying what they're saying to the subjects is they're saying, okay, at some point in every 10-second period, you're going to hit this button with your right hand or this button with your left hand, and you get to decide in every whatever it is 10, 15-second interval when you're going to do it. Okay, and so. And so we have the intervals on the clock for you, and just do it when you're going to do it. But don't do it until you've decided. But the moment you decide which hand you're going to use, then do it. Okay? And so they sit there, and they go like that. And about like a third of a second before they do it, a little arrow will come on above their head that points they're about to do their right hand or they're about to do their left hand. And so what they're saying then is, well, okay, before the person even decides, the computer apparently is able to detect the cascade of neurons and the direction it's going before they even make their decision. But, I think that is, but like this guy I'm telling you, he would say, well, yeah, but that we don't know that cascade of neurons, there could be some other factor that we're not understanding that just causes both to happen. It's like the people showing up in the train station.
Right.
Okay. So, who knows? But it seems to me that if you were conscious about it, you could kind of fool yourself into, I'm going to do this and at the last second, one, and fool the computer. And if you practice, maybe you would even get to the point where that you could make the computer, you could decide which way it was going to pick, regardless. And if that's true, then that experiment is really defunct. I mean, because then it's not really figuring out, it's what it's measuring is not a measure of, our free will or whatever. So that's why I want to try and do it.
Okay. All right. So, I like it.
Yeah.
How does staying on the consciousness subject, how does quantum mechanics work within that realm? Is there a correlation between the two? Because I know I've heard you, you're a great public speaker. You're one of the best public speakers I know. Your ability to memorize your speech, you'll take a 30-minute dialogue or monologue and just memorize it and replicate it multiple times.
Right.
Almost the same.
Yeah.
But so we've talked a lot about quantum mechanics, and this even more so kind of blows my mind, and I start to go cross-eyed when you get into this world. But how does that, as far as I know you've talked about if you take an atom, you split it in two, and you put them on opposite sides of the globe. If you spin them one direction and then you change the direction of that atom, they'll basically sync to each other, correct? I'm probably butchering that.
It's what it is two particles that are on the quantum level, typically like an atom, okay? If they are come in contact with each other in some sense, you can separate them by any distance that you want to. And then if you look at the certain properties of this atom, it will instantly cause this guy over here to have the inverse property, or the
so it's opposite. Okay.
Yeah, it's the opposite. Now the thing is at first blush, you say, okay, well, they affected each other when they were together, and then you take them apart, and well, okay, so just because you look at this one, if this one's heads, this one's always tails, big deal. You know, that just seems like that happened, something happened there. But the thing is what we can do with that is that we can, the way we measure, like let's say this property called spin, right? So we can move a particle with a particular spin through a detector, and it will be 50-50. It's always up or down. Okay, but what we can do is we can create these gates that sort of make it so that it like it can only go at a certain angle that will cause the spin to be something different. Okay, so I mean, it's a little complicated to explain, but so basically the way we measure it can affect whether it ends up being spin up or spin down. So in layman's terms, the simplest way to say it is that we know and we can prove and we can show that how we use the detector can cause, like it could be spin up, and the way it comes through the detector, we force it to be spin down, let's say. Okay, you could sort of, but that is probabilistic, okay, and the way we set it up, it would still be probabilistic, but the way we can set it up, we can measure it so that we know what those probabilities are of being spin up or spin down, and especially then when we randomize it. So what happens is we can randomize it over here in such a way, so these two atoms, they come together and now they're flying apart, right? And so we randomize the way we measure the spin of this particle up here, so we know we're affecting its spin. We're affecting how it's spinning, right? In a probabilistic way, and so the thing is if what happened was this guy is spin up and this guy is spin down, and the way we measure it here probabilistically makes it so that we're changing it in a probabilistic way. Then over here, this detector over here, that shouldn't affect what this guy is. So if they split and this guy is up and this guy is down, and then we affect the probability of this being up over here, it shouldn't affect the probability. This should just stay, well, okay, this one's down, right? And we should always just detect that, right? But that's not what happens. So what happens is no matter what we do, no matter how we measure it, where we know we're affecting the probability of it being up or down, then this guy here always gets changed in such a way that we know probabilistically it's always 50-50. So in other words, there's no way that could have happened. It's like, okay, well, sometimes we change it to be heads, sometimes we don't. So how does this guy over here from this long distance, or up or down, so when we randomly change it up or down over here, how does this guy know to flip in such a way that it'll always be the opposite of this guy over here?
Right.
And it always is.
So what does that what does that mean to you?
That means is that somehow, this is what entanglement is. It's somehow there's something about quantum reality that somehow, through even an infinite distance, that information is somehow exchanged between these two. So there's some sense in which the distance of space between them is somehow negated. And no one knows the answer to that. I mean, nobody knows the answer to that. Okay, so that's still a mystery. Now you can't. The thing is it technically doesn't violate Einstein's theory of special relativity in terms of the speed of light, because that says that only information can be sent at the speed of light. Now, while you can say, okay, well, this particle is sending information to this particle or something, okay, you could make that argument, but we can't use that to send any information. So, because no matter what, like if you send me a particle, I mean, yes, if we're light years apart and the two atoms come flying, one to you and one to me, okay, I can open my box and I can look at mine and I can see, well, it's heads or it's up, if you're using heads and tails, okay, it's up. I know then that yours is down.
Right.
And no matter what I do to measure mine, if I measure a certain way and you're not doing anything to measure yours, okay, and I measure mine, then no matter what mine is, yours will be the opposite of it. But the thing is because the initial thing is random to begin with, there's nothing that we can do. There's no way I can use that to send you information. You see what I'm saying?
Right.
Okay. So
you're talking about as actually like utilizing it as a communication source. Gotcha.
So like there's no way, like if I manipulate mine, so
Morse code.
And let me say,
we could do Morse code.
If
we do Morse code,
right? Yeah. And I am saying things in a way that are deeply or not entirely accurate, but I'm doing it to simplify. Okay.
No, I appreciate that. Thank you.
But let's just say, let's say I can change mine so that the way it comes to me, I have some probability of making it heads or tails, right? The thing is so you'll get the opposite, but you have no way of knowing how I even manipulated mine.
Right.
So for all you know, it's just yours was up or down and mine was the opposite.
Right.
So there's no way to send code or whatever.
Mm-hmm.
Some people now are claiming that maybe there is a way, and I'm not up on that yet, that kind of cutting edge stuff. But yeah, nobody understands that. But I think what's more perplexing is it's the observation that makes it come true.
Right. So like the particles will act like they know they're being observed.
Right. That's right. So that's the only way I know to put it. Yeah.
How the hell does that happen?
Yeah.
Right?
So right.
Yeah.
Yeah. I mean, like you can. So if you send, particles through a double slit, and on the backside there's a screen. Okay. So you think of a particle like a little ball, right? So it goes through one slit or it goes through the other slit, and it hits the screen on the back, and it leaves a little dot of light. So if you send them through one at a time, those little dots of light will, over time, they'll add up, and you'll basically get these 2 bars of light, right? Okay. So when you send a wave through, when you send light through, the wave, goes through both at the same time, and then when it emerges on the other side, it's like as if each one becomes its own wavefront, and then those waves, as they propagate toward that screen, interfere with each other. Mm-hmm. And so where you have peaks, you have light, and where you don't have peaks, you don't have light. And so you get this interference pattern. Okay. But that doesn't seem like that should happen with particles or even with single photons, mm-hmm. just one photon by itself.
Right.
But you send electrons, or you send even, at this point, they're sending things called buckyballs, like these giant molecules of carbon through, okay? And even they do this. They display this behavior. So what happens is when you send these single particles through, they act as if they're a wave if you don't look. Okay, so if you don't do...
Like, are we talking about, like, peekaboo here, or did they just, like, leave the room?
Okay, what I mean by it, they call it the measurement problem. What it means is if you do something... that anything at all that would allow you to know mm-hmm. which slit that particle went through, then what will happen is it will just create 2 bars of light.
Okay.
But if you don't do something, if you have no way of knowing which slit it goes through, and you just wait on it, to keep hitting the screen, then what will happen is an interference pattern will be created. Okay? But if you do anything that lets you know, if you try and watch or anything at all that will let you know, which slit it went through, then it just creates 2 bars of light. Okay?
And we still don't know why.
And you can even, and get this, you can even do it to like where, okay, so, you send this atom, and instead of it being 2 slits, it's like it goes through one channel or another channel where it ends up in like this mirrored box, right? That it's just bouncing around, right? So it's got to be in one of those 2 boxes, right? And so, if you don't look, and you can leave it there for a while, right? If you don't look, and then you open up both boxes, it'll come out as though it were a wave from both boxes, and it'll create an interference pattern.
Okay.
Right? But if you check which box it's in, and even if you check, you get the wrong box. It's not in that box. Okay? So there's nothing you could have done to have affected the fact that this guy is in this box. It was not touched at all. Okay? Nothing, there was no physical thing that could have as we understand it, could have affected that. You looked in the wrong box.
Right.
You looked in the one that was empty. But now, when you open those two boxes, boom, it'll just be one particle coming out of this one. Okay? And so, yes, we've even done them now to the point where, like, there's just one called the eraser experiment. And the idea is, so you send like this photon or a particle through a crystal that causes it to be split, right? And so one of them will go down this path, the other will go down this path. And so down here, like, you'll have these detectors down here, okay, that will tell you basically, which channel it's gone through. And so if it hits detector A, then this photon's going to hit at side A, right? So if you do that and you keep sending these photons, it'll just create these two bars of light, right? But then you can have the same setup basically. You can drop these two silvered mirrors, right? Such that, so what happens is when the photon hits this silvered mirror, half the time it'll go right through.
Okay.
But then half the time it'll bounce off at a 45-degree angle, hit this one, bounce off, and hit that detector. Hit this detector over here.
Yeah.
So that means that now by dropping, and the same thing with the other channel. So everything's the same.
Mm-hmm.
Except now you've just put these two silvered mirrors here. That's it. That's all you've done, okay? Now an interference pattern will be created because now you can't rely on these two detectors to tell you which channel this photon went through. You can't rely on it anymore. And so now an interference pattern will be created. And the crazy thing is that they can make the distance to these detectors here further than the distance to this screen. So in other words, the photons that hit the screen, they hit the screen before its sister proton even gets to these detectors here. And yet changing that setup there will change the pattern that it creates. So and that's mind-boggling.
So like what does that mean for us? Like as far as like, how do you think that connects to us as like we're just atoms.
I don't know. It's just, it's, I mean, some people have said, well, so the wave function, which is the mathematical description, it's as though the particle is the wave function, even though the wave function, it's a mathematical description. It's something you write on paper and you could graph it, or whatever, but it's a probabilistic function. So it's like, the particle is a probability wave moving through space. What the hell would that be?
Right.
And so if you accept that, then with experiments like this, it's almost like saying, like some have suggested, well, maybe the probability wave, maybe what it does is it propagates forward and backward in time. And it does both. And so somehow it can affect each other forward and backward.
So what you're saying is like our time is it's not bound by the
right. And some have suggested that one of the ideas is the many worlds theory. So that's the idea that what really happens is everything that can happen does happen. Okay.
Yeah.
And so what happens is we just find ourselves, whatever outcome we see, that just happens to be the branch of reality that we're in, basically.
Gotcha.
Okay. And, Sean Carroll, he's a big proponent of that.
Who's Sean Carroll?
He's a pretty famous physicist who does a lot of YouTubes now and everything. He's at Caltech.
Okay.
He believes in that. But the most popular interpretation of quantum mechanics, it's called the Copenhagen interpretation. It was Niels Bohr, who was one of the founders. And the interpretation is simply that these particles simply do not take on their properties as a particle until they're observed. Once they're observed, that forces them, it forces the wave function to collapse.
Okay.
Into this particle.
But we still don't know why
why it collapses.
Or how they know that they're being observed.
Right. We don't understand it. We don't know why. I mean, technically, they just call it the measurement problem.
So, like, if you're measuring, then it will do.
Right. The moment you do something to take a measurement, like in the case of the double slit, to see which slit it's going through is some kind of measurement of some kind. And the moment you do that, it collapses. So, it technically doesn't require consciousness in the sense of, like, if you set up a detector, and you've created it so that if someone wanted to, they could know which slit it goes through, and then that person leaves the room and doesn't pay attention, well, it'll still just create the 2 bars of light.
Right.
If you make it so it can't do that, then it'll create the interference pattern, whether somebody's watching or not. So they tend to call it the measurement problem. But oddly enough, a measurement is a collection of information, and information is something that seems analyzed by consciousness. So it's like, what could be said is anything that you would do that would allow a conscious observer to go back and check causes the wave function to collapse. Right.
Well, to bring this thing full circle.
Yeah.
Well, I share with you kind of my emotions and reactions to the telescope pictures. What was your reaction?
I haven't seen them all, but my reaction was, this is what we expected. It would look, I had a sense of awe. They pointed out there was one galaxy that was like 13 billion years old. It's red. I thought to myself, my God, I mean, we're seeing light that's 13 billion years old. I mean, so that light started its journey here long, long before our solar system even existed.
Right.
And that's, so when Jesus was doing his Sermon on the Mount, that light was relative to the distance it traveled, almost here. Okay. Almost here. I mean, It was like, it's just, inches away compared to its journey, but was still 2,000 light years away,
Right.
But it started its journey. And that to me is like, that's astounding that we can know that, that we can discover that. And it does seem that the more that we find this idea of design with lots of randomness in there, but
chaos,
nevertheless, I mean, everything that we discover seems to indicate, like things like, if you just change the mass of a proton by the tiniest amount, the entire universe just wouldn't exist. Okay, if you change the strength of the strong nuclear force or the gravitational force, I mean, there's several dozen of them at this point. If you change those parameters even the tiniest little bit, reality as we know it just would not exist at all. Okay, certainly not one that could have life.
Right.
And that is sort of astounding. And so in that sense, it does seem like maybe there is something to, maybe this sheet in the higher floating in the higher reality was created by that higher reality for the very purpose of interacting with it to create this thing that we call a consciousness within the bounds of this reality, and that's the real experiment. That's the, whatever created that had its purposes, and if that's God,
or what we've called God, right?
Yeah, or maybe a lot of people believe that that we're just connected to that thing, and we're just, so a lot of people say, well, it's like a simulation in the sense that you've immersed yourself in it and you've robbed yourself of the memories of before you were in it. Ryan is big on that, I think.
Right.
And that I can imagine that. I can imagine saying, okay, we can choose to put ourselves in a simulation that will take away our memory of the world we came from, but it wouldn't rob us of our free will entirely. And as a matter of fact, I mean, maybe what we see from our perspective here, maybe what we're seeing as, our brains just seem to do things and we make choices that we don't even really understand, is really just our higher selves making those choices in a way it can understand, but that we don't. So, I mean, you can imagine, like, when you're in a dream, you do things that are nonsensical.
Right.
You do things that don't make sense. And you don't know why you do them in the dream, So I don't know, those are big questions. I started this whole journey with, I'm going to discover the truth.
Right.
No more bullshit from religion. No, I'm going to go on this journey of truth for myself, and I'm going to find the truth.
Right.
And
well, it's like
here's what I can say. I mean, that journey has been a success in this way, in that I've gotten far enough. I don't know what the properties of quantum mechanics really imply about consciousness and the possibility of a supreme being, but nobody else does either.
Right.
I know that much.
Do you think there's arrogance in the sense of like knowing like absolutely without a doubt of anything? Like whether or not there is a God or creator or supreme being or whatever it may be, like I don't feel like you're saying this as a fact. I think that you're saying it as an opinion of what you believe reality to be, from your observation as a physicist and mathematician. But
all I can say is that it seems to make more sense to me that there's something like what we would call some intelligent sort of creator when I consider everything. But a lot of what I'm considering are not things that are empirically observable, and they're things that that we have at present anyway. We have no way of empirically observing, so they're not scientific in that sense. But they're also not observable for anybody else either. And all I can say is that the arguments that I make seem to make more sense than not. But what if that higher reality and the intersection with this sort of sub-reality is what creates the consciousness, and outside of the two together, it just doesn't exist?
Yeah.
I mean, that's a possibility.
Sure.
Who knows?
Yeah.
I don't know. Maybe when we die, that's it. We're just dead. There's nothing else, And I think probably it's true that most people would prefer to believe that there's some sense in which we go on. And so, so I guess what I'm saying there is I could kind of be right about that, and there's still no life after death. I don't know.
Right. Yeah.
I mean, so, I don't know. Which is why I'm trying to make the death escape velocity through David Sinclair.
Or at least trying to do it as long, live life as long as you possibly can.
Maybe if I can just make it to that point where they can reprogram and I have no senescent cells, and who knows how long I'll make it. And if I can then get my brain uploaded into a supercomputer and we're a multi-planet species at that point, it's on lots of computers and everything. Hey, maybe I have a shot at millions of years. I don't know.
There you go. One of the things I love is that when we have a conversation, my brain is hurting after because you have a way of explaining things, and I just always really enjoy our conversations. And man, I really appreciate you coming on, man, and educating us and sharing your gift of knowledge within these this world of science and physics and mathematics. And so thank you so much, man. I really appreciate you coming on.
You're welcome. It was a fun time.
It was. Thank you.